Hello everyone, my name is Zico. In this video I explain scalable Laplacian K-modes from our work in NIPS 2018. So we advocate the Laplacian K-modes for joint clustering and mode estimation. It contains the first term which estimates the mode of each cluster like mean shift, and a well-known Laplacian regularizer which is well cited for spectral clustering and semi-supervised learning. The task is to minimize this combined energy subject to the discrete assignment variable and simplex constraint. So while Laplacian K-modes, it can handle the non-convex clusters like spectral clustering. It gives the prototype as mode from the valid data points. It can be useful for manifold structured high-dimensional inputs such as images. In this example, we have several semantic classes, and the modes actually gives the most frequent semantic information of each cluster, unlike means, which is useless representatives in this case. So Laplacian K-mode is a challenging optimization problem. Well-known spectral relaxation can be used, but it has the limitation over computation and memory load when the n is very large, and making it scalable is an active research. Relaxing the integer constraint gives the convex relaxation. However, they still need to solve over all the variables jointly with an overhead of simplex projection. Our main contribution is to give a concave relaxation, thus making it a parallel structure and avoid the expensive simplex projection. So if we take the Laplacian, we can write it in this two form, which are equal at the vertices of the simplex. However, they are not same for the relaxed domain, and we notice that we don't relax this term, which give us a tighter relaxation to the original Laplacian objective. So we take this term, and this is a concave function, thus optimizing the first order approximation decreases the original energy at each iteration. And this concave relaxation can be useful for Laplacian regularizer in any other context. We can also bound the K-modes in this way, and we introduce a convex entropy term which help us avoid expensive projection step. So this is our bound, and this is sum of independent function. We solve it for each point independently with guaranteed convergence, and thus make it scalable. And this is the closed form solution of our Z update. We also show that the modes can be found from this proximal optimization, and interestingly this is already in the Z update, but with a soft approximation of the max, which is linear overhead, and it doesn't need the gradient ascent, and it is independent of feature dimension and can be useful for arbitrary kernels. These are some of the results, and we obtain competitive performance in terms of speed and accuracy, and we also give better timing than basic k-means because our updates are independent of the dimension. We also consistently obtain lower values for the discrete Laplacian objective at convergence, and this also indicates that our Laplacian regularizer is tighter than a direct convex relaxation. And that's all. Thank you so much.